This video is for Chemistry in the Earth System, Unit 3.33, Covalent Bonding. Our first essential question: how do valence electrons and orbital hybridization influence the formation and properties of covalent bonds? Our first main idea today: coordinate covalent bonds. Covalent bonds form when an atom shares valence electrons with another atom. For example, in a molecule of methane, which is CH4 on the screen here, a carbon atom forms a single bond with each of 4 hydrogen atoms. Each single bond is made up of 1 electron from the carbon atom and 1 electron from a hydrogen atom. Likewise, each single bond in ammonia, which is NH3, is composed of 1 electron from the nitrogen atom and 1 electron from a hydrogen atom. The nitrogen atom in NH3 has a complete octet. But the question is, can the nitrogen atom form a 4th bond to make the polyatomic ion ammonium, which is NH4+? The answer is yes. The nitrogen atom in ammonia has a non-bonding pair of electrons. The nitrogen atom uses this pair of its own electrons to form a single bond with a hydrogen ion. An ion which has no electrons. A covalent bond in which both electrons come from only one of the atoms is a coordinate covalent bond. A coordinate covalent bond is formed when one molecule donates its lone electron pair to another molecule. A molecule of ammonia shares its lone pair of electrons with a molecule of boron, for example, in boron trifluoride, to form an ammonia-boron trifluoride complex. Next main idea: resonance structures. Lewis structures often show the correct bonding in a molecule, but as with any model, Lewis structures have their limitations. In some molecules that have double or triple bonds, the locations of the bonds may vary. We say that these molecules exhibit resonance. They cannot be represented by only one Lewis structure. Resonance structures represent all of the possible positions of electrons in a molecule's chemical bonds. For example, ozone, which is O3, is an important molecule for life on Earth. Ozone helps to shield Earth's surface from harmful ultraviolet light. The Lewis structure of an ozone molecule has a central oxygen atom joined to one oxygen atom by a single bond and to another oxygen atom by a double bond. Covalent bonding and properties of substances. Many covalently bonded compounds, such as methane and carbon dioxide, are gases at room temperature and standard pressure. Others, such as water, are liquids at room temperature and standard pressure. When atoms bond covalently, they can form molecules of simple compounds that have low melting points and low boiling points. However, some atoms that bond covalently do not form individual molecules. Instead, they form a large network of bonded atoms. These substances are referred to as network solids or network compounds. For example, silicon dioxide or silica, which is SiO2, does not exist as individual molecules. Each silicon bonds with 4 oxygen atoms, and each oxygen atom bonds with 2 silicon atoms. The result is a network compound that is very hard and has a very high melting point, which is why glass is made from silica. Our next main idea: hybridization in carbon atoms. Each carbon atom can form up to 4 bonds with other atoms. The Lewis structure of carbon shows us how this works. Carbon has 4 single electrons that can be used to form chemical bonds. And a carbon atom can complete its octet in several ways. It can form 4 single bonds, 2 double bonds, a double bond and 2 single bonds, or a triple bond and 1 single bond. However, the orbital diagram for a carbon atom tells a different story. The valence electrons are not arranged as 4 single unpaired electrons. 2 of the electrons are paired in the 2s orbital. The other 2 electrons are unpaired in the 2p orbital. So, how does the carbon atom in a methane molecule form 4 identical single bonds? First, an electron from the 2s orbital enters the empty 2p orbital. It jumps. This gives the carbon atom 4 unpaired electrons. But these electrons are in different types of orbitals, so they cannot form 4 identical bonds. However, the orbitals are combined in a process that we call hybridization, and the result is 4 identical orbitals. The orbitals are equal in energy. Because they formed from 1s and 3p orbitals on the same main energy level, these 4 orbitals are called sp3 hybrid orbitals. They can allow a carbon atom to form 4 identical single bonds. So, in order to form a double bond and 2 single bonds, a carbon atom needs to keep 1 electron in a p orbital. The s and 2 of the p orbitals hybridize. So, the carbon atom in methanol, which is H2CO, uses sp2 hybrid orbitals. To form a triple bond or 2 double bonds, a carbon atom needs to keep 2 electrons in p orbitals. So the s and 1p orbital hybridize. And in this case, the carbon atoms in hydrogen cyanide, which is HCN, and in carbon dioxide use sp hybrid orbitals. To form a double bond and 2 single bonds, a carbon atom needs to keep 1 electron in a p orbital. The s and 2 of the p orbitals hybridize. So again, like we said earlier, the carbon in methanol, which is H2CO, uses sp2 hybrid orbitals, as seen on the screen here. And again, just to give a visual to what we've already said, in order to form a triple bond or 2 double bonds, a carbon atom needs to keep 2 electrons in p orbitals. The s and 1 of the p orbitals hybridize. And in this case, the carbon atoms in hydrogen cyanide, which is HCN on the screen here, or in carbon dioxide, CO2, use sp hybrid orbitals. At this point, you should be able to generate a full and appropriate response to today's essential question. How do valence electrons and orbital hybridization influence the formation and properties of covalent bonds?